Okay, so let's look at public key encryption. So public key encryption was set up, or the foundations of it were laid in a classic paper from Diffie-Hellman on a key exchange method, and where it was proposed that we could set up a trapdoor method to allow us to be able to create a function where if we knew a secret, we would fall through this trapdoor and reveal something. And that was in 1976. And then Rivest, Shamir and Alderman in 1977 came up with the RSA method, which is still used these days. So let's have a look at the main methods that we have for our public key encryption. Obviously, we have what's called a difficult problem to solve. If we don't have a secret, then we cannot solve the problem in a reasonable time. It's very expensive. But if we do have a secret, then it makes it fairly easy to solve the puzzle. So with public key encryption, we have a key pair. And the key pair is that we have a private key and then we have a public key. So Bob and Alice can have their own key pairs. Everyone can know Bob's public key, but he keeps his private key secret. The three main methods that are often used when it comes to public key encryption, or the three main puzzles that we need to solve, are integer factorization, discrete logs, and elliptic curve methods. The discrete log method is hardly ever used these days because it's becoming more computationally difficult. But we still use the RSA method that this is based on, typically in identifying websites. So the method here is called Elgamal that we can use, and it's kinda still used because we use it in terms of digital signatures. And for elliptic curve, we have curves such as 25519 and SEPT256K1 as we get in Bitcoin. So these are the three main methods that we use. When it comes to this, the difficult problem is that we have two prime numbers and we create what's called a modulus. And the difficulty is it's difficult to find the two prime numbers which created a given modulus. With this method, we use discrete logs such as this. G, a generator value, typically 2 or 3 or 5, to the power of a secret, and then mod P, where P is a large prime number, typically a couple of thousand bits. And the difficulty is to find the value of X, even though we know Y, G, and P. And elliptic curve methods use a curve that looks like this. And this gives us amazing performance compared to the other two methods. So while we talk about thousands of bits for the prime numbers, here, we might only talk about 160 bits or 256 bits for elliptic curve methods. So these are seen to be much more efficient these days compared to these ones. But of course, they are all at risk against quantum computers, which do not see these methods as a hard problem anymore. So we probably need to move away from these methods eventually. So let's look at what we do with public key encryption. So this is the methods that we have. Let's look at the usage. There are three main things that we do for public key. First one is where we encrypt data. So here's Bob and here is Alice. So if we have some data to encrypt, then if we use our pink key, and then Alice has a private key, and she has her public key. To encrypt data for Alice, then Bob will take Alice's public key and decrypt the data. When that's sent over, it is then her private key which is then used to decrypt the data. Okay, so in this way we can encrypt data for Alice with her public key and then use her private key. The downside of this is that because of the maths, the complexity of the methods used, then if this is large amounts of data, it can be computationally difficult. And we would typically not use this method to encrypt large amounts of data. What we typically do is something else. So if we have Bob and Alice again, one way that we can share a secret key that they might use. Let's say that we have this key here. So let's say that Bob wants to get this encryption key over to Alice. And this is going to be the key that they'll use to encrypt data or to encrypt their communication. So for this, again, what we can do is that we can take Alice's public key and we can encrypt this secret key here over to Alice, and then Alice would just use her private key to be able to decrypt the resulting encrypted value back to the shared symmetric key. So we'll perhaps show this as a different type of key. This is our symmetric key here that we want to use for the session, and that will be something like an AES key. So this is known as key exchange. This is known as public key encryption. First usage, second usage, and the third usage is in proof of identity, where Bob can prove his identity by signing with his private key. Okay, so let's take Bob and Alice again. Bob and Alice. And now Bob wants to prove that he signed a message to Alice. So what he does is he takes the data and then he will take a hash of the data and then will encrypt it with the hash with his private key. So he will take his private key here and encrypt the hash with his private key. Then on the other side, Alice will take the data and recreate the hash. So we get the data, recreate the hash, and then we'll take Bob's encrypted hash version there and decrypt that with his public key. So if we have his public key here, which is known, Alice will take that public key, decrypt the hash, and then check that the hashes are the same. If they are the same, then she has proven that it was Bob who signed the message. So that's the third form that we use public key encryption for: proof of identity, key exchange, and encryption. So now let's look a little bit in more detail at the main methods involved. Okay, so these are our methods that we have. There's the usage there. We have a signing process. This is also known as signing. This is key exchange, and this is encryption. These are the main methods that we will use. In terms of getting the keys for Bob and Alice, well, what we can have is we have digital certificates. And a digital certificate is something that has been signed by a trusted entity but contains the keys that we require. So we can get one that contains the private key and also the public key. This is a secret digital certificate and is only used when we need to sign for something or within key exchange. Typically, we would export that certificate into a form that only contained the public key. And this is a distributable form that we have for exposing Bob's public key to Alice. Again, this will be signed by a trusted entity, Trent, that both Bob and Alice trust. So when Bob wants to pass his public key to Alice, he will send over a digital certificate signed by Trent, and she will check that it has been signed by Trent, just like here, and then we'll be able to get Bob's public key from there. The other way we can do this is that we can have a keyring with all of the public keys that Alice might use. So she doesn't have to keep requesting them. So Bob could publish his public key on a repository or send it to Alice, and she would put it onto her keyring so that when she was sending information to Bob, she would look at the public key on her keyring. And along with this, she could obviously have, as long as it was secure, her private key on the same keyring here. So this would be kept secure, and where she had all the public keys that she wanted to use and had her own private key for signing. Okay, so that's how we would distribute the public key to Alice. Now let's look at the methods that we use. And the first method is good old RSA. With RSA, what we do is that we start off with two prime numbers, P and Q, and we create a modulus from that. And we typically define this modulus as n, which is P times Q. The difficulty is that for this modulus, it's difficult to find P and Q if P and Q are large. Typically, there would be 1000-bit prime numbers, and this would be a 2000-bit modulus. We would define that as 2K RSA. The next thing that we need to do is we need to define our encryption keys. And RSA is an exponential cipher. We take our message and we raise it to the power of an encryption key, then take mod of n for the cipher, and to get the message back we take the cipher to the power of d mod n. Remember that mod n is the remainder of divide by n. We're not interested in the actual value that is, but only in the remainder. Okay, so this is the way that we would do our encryption and our decryption. So we need to find E and D. So the first thing that we do is that we work out a value called phi, and phi is P minus 1 times Q minus 1, and it gives us a result. Then we select a value of E which does not share any factors with phi. We would often write that GCD of phi and E is equal to 1. So there is no factor in E that's in the value of phi, which is P minus 1, Q minus 1. Then we work out D, this here, to make sure that D times E mod of phi is equal to 1. And this will make this work. And D, the calculation D, is actually inverse mod of E, the inverse of E mod n. This is a standard calculation that we often do in public key encryption, and it basically finds the value when you multiply E by that value and then take the mod of phi, you'll end up with 1. And this will make this part correct. So let's take a simple example of this. That's that one there. From there. Okay, so a simple example can be where we have a value of, say, P equal to 3 and Q equal to 11. So the n becomes 33. So the modulus in this case is a value of 33. Then we can work out phi, and phi is equal to 2 times 10, which is 20. The factors that we get in 20 are 2, not 3, 4 of course, 5, and so on. So we can't pick these values for E, so we might pick a value of 3. So 3 is our encryption key. 3 and 33 is the encryption key. Now D times E mod of 20 is equal to 1. And rather than doing this function here, it's quite simple to see that if d is 7, 7 times 3 is 21, mod 20 equals 1. So our decryption key is 711. Okay, so when we take our message and raise it to the power of 3, then take mod 33, that gives us our cipher. We then take that cipher and raise it to the power of 7, then take mod of 33, and we will get our message back again. And this is the power of the RSA algorithm. It's still highly relevant these days, but the computing power that we need is actually quite large. The method that we most often use these days is called elliptic curve. And with elliptic curve, we have y squared is equal to x cubed plus 8x plus b mod p. This is the standard equation that we have for our elliptic curve, or one of the equations that we have for elliptic curve. The mod p makes sure that we're only dealing with integer values for our elliptic curve. But a shape in the non-mod form will look a bit like this, and where we have a point here, and when we add points on the elliptic curve, we'll always get another point on the elliptic curve. So the elliptic curve itself has basic parameters a, b, p, the prime number, n, which is the number of points that we can have on the elliptic curve, called the order. It's the order. P is the prime number, A and B are here, and G. G is what's called the base point, and it's almost like the starting point for all our elliptic curve operations that both Bob and Alice know. So this gives us our basic parameter for our curve. So common curves are curve 25519. That uses a prime number of 2 to the power of 255 minus 19. And also SEPT 256K, which is used in Bitcoin transactions. So that gives us our basic curve for that. And how do we actually use this? Well, the way that we do this is that we come up with our prime number, well, our private key value n. So n is our private key. What we then do is that we come up with our public key, p is equal to n times g. So we take our base point and we add g to itself n times. So we end up with a point on the elliptic curve p here, an xy point that's equal to ng, where n is our private key, g is the base point, and p is g added n times. An elliptic curve, the adding operation is a very easy operation to do, and we always end up with another point on the elliptic curve. So with this, anyone can know our public key, anyone can know our value of g, anyone can know the parameters here, but no one should know this private key. Only with this private key can we actually sign for messages. One way that we do this is with what's called elliptic curve DSA, or digital signature algorithm. With this, we take a private key and we can sign for a transaction. and generate our public key. So we don't have to create prime numbers. What we do is we create a random number, and then we can create our public key from that. The way that Bitcoin works is that when Bob wants to send Alice a transaction, then Bob will take the Bitcoin, will take his private key value, and then sign the transaction with his private key. And then his identity is actually derived from his signature, so that everyone can know his public key, so that that transaction can be instantly known that it relates back to his private key here. So that's elliptic curve Diffie-Hellman we have here. Let's see if we can now use all of these elements together to see if we can send some trusted data from Bob to Alice. Okay, so for this we'll look at what's called Pretty Good Privacy, or PGP, but it's really just an example of how we can integrate all of these methods together. So initially we'll have some data, and then Bob takes a hash of that data, and then we'll create an encrypted hashed version using his private key. Okay, so we take the data, the message, we take a hash of it, and then we will create an encrypted version of the hash. This is really a signature that we have. So now what we'll do is that we'll take this data and we'll add on the encrypted hash into the message. And now this could be a large amount of data. So what we want to do is to then encrypt this with symmetric key encryption. So this is our encryption here, and we have our data in there, and the encrypted hash, and then Bob will create a new symmetric key, especially for this message here, and we'll encrypt the whole thing with the symmetric key. Now Bob then takes that symmetric key and then encrypts with Alice's public key. So if we have Alice here, and Alice's public key will be used to encrypt this symmetric key. And the whole thing can be sent over to Alice to then read and decrypt. So here we have the encrypted message, and we also have the encrypted symmetric key, which has been encrypted with Alice's public key. So the easy thing now is now that Alice can decrypt that key, that symmetric key, with her private key. So she will take her private key and then decrypt this to give the symmetric key, which will then open up the data. She does that, and in the end she'll end up with the message, and also the signed version of Bob's hash of the message. She can then read the message now, but then she'll take her own hash of the message She then takes Bob's signature and then using Bob's public key she will then be able to decrypt this hash and then end up with the same hash here. And if the two hashes match, then she knows it was Bob who signed for the message and knows that the message has not been changed in the transmission. Okay, so this has been an overview of public key encryption.